Hello friends. Here is Mr. Ramesh Chandra taking lectures on probability. This is our third lecture, and we will have full lecture series on the topic probability from very basic that you have seen to very advanced level. These are our books that you have seen in our previous lectures. We are having discussion on events and types of event like impossible and sure event, simple event, compound event, and then we have algebra of event. In the case of algebra we have addition, subtraction, multiplication, but in the case of set theory we don't have that kind of theory. In the set theory there is union and intersection, so union, intersection and difference. So we have complementary event, union and intersection of event, difference of event, mutually exclusive event, exhaustive event, and mutually exclusive and exhaustive event. So in this lecture we are gonna learn these subtopics. At the end of this video you will be able to get these concepts. Apart from this, we have our own website where you can purchase the full lecture series on probability. That is very helpful for IIT JEE and other competitive exam. Even for KIT you can purchase. This is our website. Online courses are there. You can visit our website www.mathsarc.com. This is mathsarc.com. So let's talk about the event. First we have event. What is event? And what is the concept of event? In the last video we have learned about the experiment. When we perform experiment we have some questions in our mind, and to look out the answer of that questions we perform experiment. So event is a subset of sample space. Event is a subset of sample space. Sample space serve as a universal set for all the questions concerned with the experiment. What I have said, sample space serve as universal set for all questions concerned with the experiment. All the questions concerned with the experiment. So to understand this, we have an example. Consider the experiment of tossing a coin 2 times, and associated sample space is, what should be the sample space? S is equal to, if we toss 2 coins, then we have sample space head, tail, head, and tail. So this is the sample space. Here we are tossing coin 2 times, one after other. Even this would be the same sample space if we toss 2 coins simultaneously. Now let us talk about the event part in this sample space. Our question is, we are interested in those outcomes which correspond to the occurrence of exactly one head. In this event, suppose we are concerned about those outcomes which corresponds to the occurrence of exactly one head. So this is the question regarding the event. This is the question that we are having in our mind. So what should be in the event? So exactly one head is in this case and this case. So event must consist H, T and TH, head, tail and tail head. So this is the event regarding this question. Now let us have another example or other questions related to experiment. First question we have, number of tail is exactly 2. Number of tails is exactly 2. Twice. Now let's say second question we have for the event. Number of head at least 1. Number of head at least once. Third question we have, Number of tail is at most 2. Number of tails at most twice. And the last question we have, number of head is more than 2. Number of heads are more than 2, more than twice. These are the questions that we have in our mind. So these become the subsets of the sample spaces. Hence these are the events. And events are denoted by capital letters. So let's say we denoted by E1 event. Call this be E1. E1 as event 1. Number of tail is exactly twice. So in this event what we will have? Tail as only element in this event. Now in event number 2, number of head at least 1. Call this be event number 2. So in this event what we will have? Number of head at least 1. So we will have head tail, tail head and head. So this is event number 2. Now similarly we have event number 3. Number of tail at most twice. Number of tail at most twice. So for this what we will have? Head. Can we have this? Yes, since it is having condition of at most, so we can have head. In this case 0 tails are there. Then head tail, tail head, then we have tail. And in the last one event, call this be E4, no heads are more than twice. Number of heads are more than twice. Is there any outcome that have more than 2 head? No. So this event E4 do not contain any outcome. This is an empty set. There is nothing in it. And if you observe third event, that is E3, then you will get this is the sample space. You will get the E3 event as a sample space. So you can see sample space is serving as universal set for all the questions concerned with the experiment. Sample space is the universal set and these become the events. So event, what is event? Events are the subset of sample space. Now we have different types of events. Let us talk about the types of event. First we have first one, that is impossible and sure event. Impossible and sure events. You can see this event, you can see E4. E4 contains no element. There is no any outcome. Hence this is an impossible event. But for the third question, number of tail at most twice. So this event will definitely occur and you can say that this is a sample space. If there is a situation like any event is becoming sample space, then that event comes under category of sure event. That must happen. If you are thinking of this question to be happen when experiment perform, then this event will must happen. Hence this become a sure event. And if we talk of fourth part, number of head are more than twice, it will never ever happen. Hence this will goes under impossible event. So there are some guidelines for impossible and sure events. What it is? First, phi is called impossible event. And second point we have sample space S is called sample space S is called sure event. Sample space S is called sure event. Let's have another example to understand these events. The number appear on the die is a multiple of 7. Let's say even event we have. The number appears on the die is a multiple of 7. Now what do you think if we roll a die? Die contain only 6 element. If we throw a die, the sample space associated with this is 1, 2, 3, 4, 5 and 6. So what do you think about even event? You will see there is no any number will appear which is multiple of 7 on the dice when event is performed. So E1 goes under impossible event. Let's say we have another event E2, that is the number appear on the dice on the dice on the die is either odd or even. Now what do you think about? You will see E2 event will contain 1, 3, 5 odd or even 2, 4, 6. So you can see this is becoming simple space. Hence E2 is sure event. Are you getting me or not? I hope you all understand what is sure event and what is impossible event. Next type we have simple event. What it is? If only one element is present in event set, then we will call this event as simple event. Like if we roll a die and want to interested in getting one only, E is an event contain only one element, hence this is a simple event. Similarly, we have another kind of event, that is compound event. These events are categorized on the basis of number of elements in the event. So if an event has more than one elements or sample point. What is this? This is similar to element. Every outcome we can also say that sample point of a sample space. If an event has more than one element or sample point of a sample space, then we can say that the event is a compound event. Let us move on another topic, that is algebra of event. Algebra of events. First we have complementary event. Complementary event. What it is? Let's have an experiment. Single throw of a die. Single throw of a die. Single throw of a die. This is our experiment. So sample space regarding the same is S 1, 2, 3, 4, 5 and 6. Now we have event associated with this as E called 1 and 2. Event E contain these elements 1 and 2. Then complementary event of E. Then complementary event of E is denoted by E or C. E to the power C. Even sometimes we also denoted by E dash. E dash. And what it would be? This would contain the element apart from 1 and 2, that is apart from 1 and 2 of the sample space, that is 3, 4, 5 and 6. You can best understand this concept by set theory. Let's say this is a sample space and this is the region of event E. This is the region of event E. Then the outer region must be a region of event E complement. E complement event E and E complemented event. Then what we will have? We will have sample space S and then event E. E will contain E will contain 1 and 2 element. So put it here 1 comma 2 and its complementary event will contain 3, 4, 5, 6. Now what are you observing in this case? What are our observation? First observation we have E union E complement. If we take union of these two, then we are getting sample space S. Second observation we have, if we take intersection of E and E complement, then we will have null set, that is empty set. Later on we will understand that the probability of sample space is equal to 1, that is probability of sure event is always 1, and such type of event, that is probability of impossible event, that is phi, this is equal to 0 of impossible event. So next topic we have here, that is union and intersection of events. Union and intersection of events. What it is? This is very similar to set theory. The event A or B. A and B are two events. So A or B, union of event A and B, and denoted as A union B. And second one we have, that is intersection, the event A and B. This is called intersection of events. So you can see or and end are exclusive. You need to understand these two differ by definition, and A and B denoted by A intersection B. This is sign of intersection, this sign of union. Even we can have definition of these two, that is, this is a collection of outcomes. Let's say outcome is W, then W must belongs to A or W belongs to B. So this is the definition of union of two events. Similarly, intersection has definition as A intersection B is the collection of W is the outcomes which are present in A belongs to A and B both. So you can see these two are very similar to set theory. Now if we plot its Venn diagram, union and intersection, let's say this is a sample space S and we have event A here and another event we have, this is event B. Then the region this whole region inside the boundary of A and B, the whole region is said to be the region of, this is the region of A union B. Similarly, if we have another example, that is event A, and we have another event B, then this common region is the region for A intersection B. The common region of A and B is the intersection of event A and B. You can see these are very similar to set theory. Next subtopic we have difference of event. Difference of events. How we subtract two events, how we subtract one event from the another. So we have here the event A but not B is the difference of event A and B, and we denoted it by A minus B. If we think of set theory, then we will have A intersection B complement. Let's have a look how we are having this A but not B. The difference of event, that is A minus B event we have. So let's say this is event A, and we have another event that is B. This is the event B. So A minus B is the, what is A minus B? This region A but not B. A but not B is the difference of event A minus B. Similarly, if we think of this region or this event, what does it do? This is B minus A. The event B but not A. So this is the region for B minus A. If we again think of A minus B, then what it is? A minus, what this region is representing? A intersection of B complement. That is the set theory. Let's have an example to understand everything correctly. So let's say we have question number 1. A die is thrown. Let A be the event. Let A be the event. An odd number turn up, and let's say B be the event. A number divisible by 3 turn up. Write the following event. First we have A or B. Second, A but not B. Third, A and B. And the fourth one, not A. Not A. You can see these two events: an odd number turn up, a number divisible by 3 turn up. So what are the elements inside the event A? A event contain odd number turn up, that is 1, 3 and 5. And what are the outcome in event B? That is number divisible by 3 turn up, that is 3 and 6. So these are the two events A and B. Now what about A or B? So A or B event will have 1, 3, 5 and 6. What about A but not B? The element of A that are not in B, that is A but not B, that is A minus B. So what should be the element in this A minus B? Element of A that are not in B. So 3 is present in B, so we will not have 3, and so in this A minus B will have 1 and 5 as elements. Now what about A and B? These are the common elements or common outcome that are present both events A and B. So what are the common outcomes? That are 3. What about not A? Not A, not in A. This is an event. Whenever we have a complementary event, this always seen with respect to sample space. So if we have not A, that is A complement or A dash, so this will have element that are not in A, that is 2, 4 and 6. I hope you get this example. Let's have another theory, mutually exclusive event. What is mutually exclusive events? So before proceeding, let's have a Venn diagram for mutually exclusive events. Let's say this is a sample space S and we have event A and another event B like this. So what we are getting here, A intersection B, we are having 5. So if we are having two event A and B such that A intersection B is 5, then we will say that A and B are mutually exclusive event. Or in another way, by definition, we can say if the occurrence of one event, if the occurrence of one event prevents the occurrence of all other events, then the events are said to be mutually exclusive. Let's say for this we may have more than 2 events as well. Let's say in this case we have 3 events A, B and another one C. So what are you getting here? A intersection B is null set, A intersection C is null set, B intersection C is also a null set. So what we can say that A, B, C are mutually exclusive event. A, B and C events are mutually exclusive event. So this is the wording of mutually exclusive event. Let us understand the same by an example. Let's have an experiment. Rolling a die. If we roll a die, then associated sample space must be 1, 2, 3, 4, 5 and 6. Now let's talk about an event A event. An odd number appears. An odd number appears. Then what must be in this event A? 1, 3, 5. Then similarly we have another event B. An even number appears. So what we will have? in this event 2, 4 and 6. Now what about we have a question related to A intersection B? Then we will have 5 as outcome. And even we can also say that A and B are disjoint events. We can also say that these are disjoint sets or disjoint events. If we think of probability of P of A intersection B, then this will be equal to 0 since it become an impossible event. If you think of a question, a outcome that is both simultaneously odd and even number, then it is impossible to get since die show either odd number or even number at the top. This time we have another case. Let's say we have simplest as an even event. In this case, let's say 1, 2, 3 and 4, and we have another event E2, that is 4, 5, 6. Then you can see, let's say this is E2 event, E2, and for even we have this even event. There's some common, 4 is common in these two events, so just put 4 here, and then 1, 2, 3 must be in only E. 1, 2, 3 must be only in E, and in E2 event that are 4 is already there, 5 and 6, 5 and 6 must be there. 1, 2, 3, 4, 5, 6. So even you can see that E1 intersection E2 not equal to 5. So if this is not equal to 5, then we can say E1 and E2 are not mutually exclusive. What we can say for E1 and E2? E1 and E2 are not mutually exclusive events. But in our case, what we can say? We can say A and B are mutually exclusive events. Let us understand the same thing by an example, by solving an example. An experiment involves rolling a pair of dice and recording the number that comes up. Describe the following event. A event we have, let's say we have A event as the sum is greater than 8, the sum is greater than 8. Now B event we have, let's say we have B event as 2 occurs on either die. 2 occur on either dice. Let's say we have another C event as the sum is at least 7. The sum is at least 7 and a multiple of a multiple of 3. Our first question we have, first question, A and B mutually exclusive and B mutually exclusive. Second question we have, B and C mutually exclusive. We have third question as A and C mutually exclusive. Exclusive. So we have these three questions. Question 1, question number 2, question number. So what do you think? First solve your own, then see the solution. An experiment involved rolling a pair of dice and recording the number that comes up. Describe the following event. A, the sum is greater than 8. So what should be in event A? Greater than 8, that must be 6 comma 3, 6 comma 4, 6 comma 5, 6 comma 6. Then what we have? Next we have 6 is on first die and 3 on another die. So what other element we have? 5 comma 6, 4 comma 6, then 3 comma 6, 9. And then what about 4 comma 5, 4 comma 6 and 5 comma 4? Is there anything? Sum is greater than 8. 6, then 5, 5 6, 5 5 also be there, 5 5 also be there, 5 4, 5 3 will not be since it is equal to 8. Then we have 4 6, 4 5, and there must be 4 4. 4 4 will not be there since. Why 4 4 not there? Since its addition is 8. So you can see these are the element inside this event A. Now what about B? B event. 2 occur on either die. So this will have 2 comma 1, 2 comma 2, 2 comma 3, 2 comma 4, 2 comma 5, 2 comma 6. Then we have 1 comma 2. We already have taken 2 comma 2. Now we have 3 comma 2, 4 comma 2, 5 comma 2, and then 6 comma 2. So these are the element inside B. Now the last C event that we have, C event as what we are having here, the sum is at least 7 and a multiple of 3. Sum should be a multiple of 3 and sum is at least 7. So what are the element inside it? Multiple of 3 and sum is at least 7. Can we have 6 comma 1? No. 6 comma 2? No. 6 comma 3? Yes. Why? Since sum is more than 7 and it is a multiple of 3, 6 comma 3, then can we have another one? No. What about 5 comma 4 divisible by 3? Can we have 5 comma 1? No. Why it is so? Since that is number less than 7. Then we have 4 comma 5. What about 4 comma 2? No. Then we have 3 comma 6. 3 comma 3? No. You can see these are the element inside C. So what about A and B? Let us think of first question. First question. A intersection B Is there a 2 comma 1? No. A's sum is greater than 8 and B 2 occur on either dice. Is there any common element in these two? Let's think of. There is no any 2 inside this. So you can see A intersection B is null set. What about A and B mutually exclusive or not? Yes. So we have yes as an answer. Now what about B and C? B intersection C. Think of 6, 3. These are the. Is there any common element you can see? Are you getting any common element? No. So B and C is still a null set. So what is the answer of this? B and C mutually exclusive or not? Yes. Now what about A and C? A intersection C. A intersection C. Just observe this. A intersection C. You can see 6 comma 3 is there. Even 5 comma 4, 4 comma 5, 4 comma 5, 4 comma 5 is also there. 5 comma 4 is also there. 4 is also there. 3 comma 6. Yes, this is also there. So you can see A intersection C is C and not equal to 5. Hence, A and C are not mutually exclusive. So, no is the answer for this question. Are you getting what is mutually exclusive or not? If A and B, which intersection is null set, then we can say that A and B are mutually exclusive. If their intersection is having some element or some outcome, then we will say that these are not mutually exclusive. Let us move on another subtopic, that is exhaustive event. What are these exhaustive events? So for this, let's have an example. Consider the experiment of throwing a die, then sample space must be 1, 2, 3, 4, 5 and 6. Now let us define the following events. Call this be even. Even event as a number less than 4 appear. A number less than 4 appear. So even set contain 1, 2, 3 as element. E2 event, that is a number greater than 2. A number greater than 2 but less than 5. Less than 5 appears. So E2 must contain a number greater than 2 but less than 5 appear. Greater than 2, that is 3 and 4. These are the only element in this event. Now let's have another event, E3, as a number greater than 4 appear. 4 appear. So what should be in E3? 5 and 6. So let's say these are the 3 events associated with this random experiment. Let us observe something. We observe that E1 union E2 union E3. 1, 2, 3, 4, 5 and 6. So what you are getting? This is a sample space. Very important. Very important. If E1, E2, E3 are such event, if we take union of all these 3 events, and get a sample space, then we can say that E1, E2, E3 are exhaustive event. E1, E2 and E3 are said to be exhaustive event. Let us think of this by Venn diagram. Let's say this is a sample space S. Then we can do, let's say this is an E1 event, and this is E2 event. Then this is E3 event, let's say E3 event, and the remaining one is E4 event. So what you are getting? E1 union E2 union E3 union E4 is equal to sample space. So what we can say that E1, E2, E3, E4 are the exhaustive events since they are making a sample space. So what is the definition of it? Let us talk about the definition. If each outcome of an experiment, if each outcome of an experiment is associated with at least one of the events E1, E2, E3 and so on En, then collectively events are said to be exhaustive. Then collectively the events are said to be exhaustive. If you think of mathematically, then you will have E1 union E2 union E3 union and so on union En is equal to sample space. In another word, event E1, E2, E3 up to En are said to be exhaustive if at least one of them necessarily occur whenever the experiment is performed. Let us talk of mutually exclusive and exhaustive events. What it is? Let us think of this case by using Venn diagram. Let's say this is a sample space S and we have different events like this. Let's say this is E1 event, E2 event, E3 event, E4 event and E5 event. What are you getting here? If we think of E1 intersection E2, this is equal to 5. So E1 and E2 are mutually exclusive. Now think of E2 intersection E4, then still we can say that this is equal to 5 and E2 and E4 are mutually exclusive. Or even in generalize, we observe, what we observe? First observation is EI intersection EJ is equal to 5, where IJ is equal to 1, 2, 3, 4 and 5. In this case, this is 1, 2, 3, 4 and 5. If this is for n, then we can say that EI intersection EJ, where IJ equal to 1, 2, 3, 4, 5 and I not equal to j. And second one observation we have, what we have? Union of EI. I is moving from 1 to 5. For this case, we are moving 1 to 5. Even for if there are n event, then this will go from 1 to n. What does it mean? E1 union E2 union E3 union E4 union E5 is equal to S. Then what we will say that E1, E2, E3, E5, E1, E2, E3, E4, E5 are mutually exclusive and exhaustive. Why we are saying exhaustive? Since if we take union of all these five, then they are becoming equal to sample space. Let's just have an example to understand it clearly. Or we have question, what it is? Two dice are thrown. Two dices are thrown. The events A, B and C are as follow. First A event we have getting an even number on the first die. Getting an even number on first dice. B event we have getting an odd number on the first die. Getting an odd number on first dice. Let's say we have C event as getting the sum of the number on the dice less than equal to 5. Getting the sum of the number on the dice is less than equal to 5. Now describe the event. First we have A but not C. Second we have A intersection B complement intersection C complement. Third we have A and B are mutually exclusive and B are mutually exclusive. Fourth we have A and B are mutually exclusive and exhaustive. And fifth one we have A equal to B complement. Sixth one A complement, B complement, C complement are mutually exclusive and exhaustive. So this is an example related to mutually exclusive and exhaustive. You can solve it your own and then look at the solution. You can pause this video for a while and look your solution whether you are getting it correctly or not. If you understand each and every concept clearly, then you will get correct answer for each and every one. Let us read it again. Two dices are thrown. The event A, B, C are as follow. A getting an even number on first die. So what about the element of A? 2, 1, 2, 3, 2, 2. Similarly 2, 6 on first die. Getting an even number on first die. 4, 1, 4, 2. Similarly 4, 6. And then we have 6, 1, 6 comma 2 and so on 6 comma 6. In this case you can see you are getting even number on first die. Similarly for B, now let us think of event B as first element is an odd number. First outcome is odd number, that is 1, 1, 1, 1, 2 and so on 1, 6. Similarly 3, 1, 3, 2 and so on 3, 6 till 3, 6. And then we have 5 comma 1, 5 comma 2 and so on 5 comma 6. These are the element in the event B. Similarly we have C. For C event, what it is? The getting the sum of the number on dices less than equal to 5. So what we can have 1 comma 1, 1 comma 2, 1 comma 3, 1 comma 4 and not 5. Then we have 2 comma 1, 2 comma 2, 3. Then we have 3 comma 1, 3 comma 2. Then we have 4 comma 1. These are the only element in set C. Now let us think of event A but not C. What about A but not C? This is A minus C. The element of A that are not in C. 2 comma 5, 2 comma 6. These are the element of A that are not in C, since their sum is greater than 5, 6, 7, 8. And for next one 4 comma 2 comma 3 and so on 4 comma 6. Similarly we have 6 comma 1, 6 comma 2 and up to 6 comma 6 as element in the set A minus C. A minus C. So you can see this is not an empty set. So A but not C is this much. Now what about A intersection B complement intersection C complement? That is element of A that are not in B and not in C. So what this B complement is, getting an odd number on first die, the complement must be getting even number on first die. So C complement must be the sum of the number on dice greater than 5. B complement is A and A complement is B. So or even you can say that A intersection B complement is equal to A. C complement getting the sum of numbers greater than 5. So if we think of A intersection B complement intersection C complement is same as A intersection C complement. Now think of A intersection C complement. A intersection C complement. A intersection C complement will give you what it will give you? Getting an even number on first dice and number sum is greater than 5, that is 6, 7, 8 and so on. First dice will have even number, that is 2, then sum. Can we have 2 comma 6? Yes. And can we have 2 comma 5? Yes, it is there. Now 2 comma 4? 2 comma 4? Yes, since the sum is getting 6. And what about 2 comma 3? No, since sum is 5. Now what about 4 comma 6? It is in 4 comma 5. It is in 4 comma 4 is also in 4 comma 3, 4 comma 2, 4 comma 1. Can we have 4 comma 1? No, since the sum is 5 equal to 5. Now think of 6 comma 1, 6 comma 2, 6 comma 3, 6 comma 4, 6 comma 5, 6 comma 6. So these are the element inside A intersection C complement. Now think of third question, that is A and B are mutually exclusive. Are these two mutually exclusive? A is getting even number on first die, B is getting odd number on first die. You can see that both cannot be happen simultaneously. So what we can say that A and B are mutually exclusive. Yes or not? Yes, they are mutually exclusive. Can we say that A and B are mutually exclusive and exhaustive? You can see what we are getting. B complement is A and A complement is B. Now if we think of A union B, then what we will get? We will get completely the sample space. So what we can say that A and B are mutually exclusive and exhaustive. So this is also a true statement. Now what about A equal to B complement? We already discussed here. A complement, A is equal to B complement. Now what about A complement, B complement, C complement are mutually exclusive and exhaustive? A complement, B complement are mutually exclusive, but B complement, C complement, this is not an mutually exclusive. You can see B complement intersection C complement not equal to 5. So the statement is false. This is false statement. I hope you enjoy this lecture. www.mathsarc.com. Thanks. Subscribe our YouTube channel so that you can get latest update and latest videos. Thank you.